Good morning, everyone. So last time we gave a few basic examples and a few basic principles of the theory of Lie groups, and today we will start with a more systematic build-up of the theory. So throughout my lecture, G will be a Lie group. So that means that G is a group and also has a manifold structure, and in such a way that the group operation and the inversion are smooth with respect to the manifold structure. Now, this has a meaning that one can use the calculus of differential geometry, in particular the calculus of differentiation, taking tangent maps on manifolds, using vector fields on manifolds, and we are going to use these techniques today to construct a map, the exponential map, which is going to be a smooth map from the tangent space at the neutral element of the group, the identity element of the group, to the group. So this will be a smooth map, and the construction of this map will be our goal today, our first goal today. Now, so what we have to do is we have to find a way to connect the tangent space at the identity element to the group as a manifold. And the idea is to do this by using vector fields and integral curves of vector fields. So I think it is a good idea to start with a quick rehearsal of what we should know about vector fields. So suppose that M is a smooth manifold, then by script V of M we'll denote the linear space of smooth vector fields of M. So this is the space of smooth sections of the tangent bundle of M. So what does this mean? So this is really the smooth vector fields. And so suppose we have an element V of this space. So what does it mean? It means that V of M is in the tangent space at M of the manifold for all M in M. And moreover, the map from M to V of M should be smooth. Now this has an interpretation in terms of local coordinates. In local coordinates, a vector field has a local representation, and in this local representation the vector field should be smooth. Another way of saying this is, well, we have this tangent bundle. Tangent bundle is defined as the disjoint union of all tangent spaces, and it has been equipped with a manifold structure in such a way that smoothness of a vector field corresponds to smoothness of the map V as a map from M to the tangent bundle. Okay, now if we have a vector field, then in a local representation this vector field may be viewed so this vector field gives a vector field, and a vector field gives an associated system of differential equations, the flow equations for that vector field. Solving these equations means determining the integral curve of the vector field through a certain point. And the possibility, so let me make a picture. We have a manifold M. And suppose that we have a vector field, so that means that at every point we have a tangent vectors. And then what is an integral curve of this vector field? An integral curve is a curve, let's say alpha of t. So it depends on the time parameter t. And what we want is that the vector field is equal equal to the tangent or the velocity vector of this parameterized curve at every point t. This is what is called an integral curve. So integral curve alpha it's a smooth map alpha from an interval to the manifold M, I an interval. The interval should contain 0. Alpha should satisfy a differential equation, and the differential equation is that if you take the velocity vector of alpha at the point t, so let this be alpha of t, then the velocity vector then the vector field at alpha of t is v at alpha of t, and this should also be equal to the velocity vector of alpha at the point t. So this should be equal to the vector field at the point alpha of t. And then usually one also specifies an initial condition, and the initial condition is specifying that at a certain point of that interval, the integral curve is at that particular point. So usually there is an initial condition specifying that alpha at 0 should be m0. M0 a given point of the manifold. And now a very important result is that if a manifold is given, if a vector field on the manifold is given, and an initial point is given, then there is a unique integral curve which has the property. So an integral curve, there is a unique integral curve for the vector field with that particular initial condition, and such that the domain, the interval where the integral curve is defined, is maximal. In other words, any other solution of this system is defined which is defined on an interval, then that particular interval will be smaller than the maximal interval. So maximal integral curve associated with the vector field v and the initial condition m0 is as above, with the interval of definition maximal. So in particular, this means that the integral curve cannot be extended beyond that given maximal interval. And now, as a consequence of the theory of ordinary differential equations, in particular, so the existence and uniqueness theorem, it follows that with these data, such a maximal integral curve always exists and is uniquely determined. So alpha exists and is uniquely determined. Now this principle will play an important role in the construction of the exponential map. The exponential map is going to be constructed through integral curves, maximal integral curves of certain vector fields. Now, but before going to the actual construction of the exponential map, it's good to have a bit of preparation. I want to discuss two operations that can be applied to integral curves of vector fields. So the first operation is, suppose that we have a diffeomorphism. So suppose that phi from M to N is a smooth diffeomorphism. Then, and suppose that V is a vector field on M, and that m naught is a specified point. So then this gives rise to an associated maximal integral curve. For v with the initial point m naught. Now all these data are given on the manifold M. But everything is defined in a coordinate invariant way. And that means that if you apply the diffeomorphism in a natural way, then the vector field on M will produce a vector field on N. The integral curve on M will produce an integral curve on N. And it's not a big surprise that maximal integral curves here then correspond to maximal integrals there. It's just a matter of checking the definitions. So let's see how the operation works for vector fields. Suppose that we have a vector field here. So we have the map phi from M to N. And we have a vector field here. So this is a vector v of M, which is contained in the tangent space at M. Then how to produce a vector there? Well, in the image point phi of M, we can take the vector that is obtained by applying the tangent map of phi at the point M to the vector v of M. So we can take here the tangent map at M of phi applied to v of M. This of course is a very natural operation. And so that will give a vector field on N, and this vector field will be called the push forward of the vector field v under the diffeomorphism phi, and it's denoted by phi lower star of v. Of course, once we understand this principle, we can write down the formula for the vector field phi lower star of v immediately. So let's do that. Maybe I should do this here. So phi lower start of v in a point N of the manifold N. Well, what should we do? We should look at the point here that corresponds to N. This is phi inverse. This is phi inverse of N. And then we can take the vector field at that particular point. And then we should apply the tangent map to get back here. So we apply the tangent map at phi inverse of N to phi. And we apply this to the given tangent vector. So this is the formula for the push forward. And now a lemma that immediately follows from the definition is that the maximal integral curve is obtained by just applying phi to the integral curve over here. So this is an important property. Fact that is easy to check from the definitions. If you take the composition of phi and alpha, so this is the curve mapping t to phi of alpha of t. This is a smooth curve in the manifold M now, the second manifold. And then the statement is that this is the maximal integral curve. Maximal integral curve for the vector field push forward of v under phi, and as the initial point one should take the image of the initial point here under the map phi. So this is phi of M naught. So this is a first way to produce maximal integral curves for vector fields by using a general principle. Now there is a second way to do this. And the second way is by doing a translation in the parametrization. So suppose that we have a manifold M. So this is a second way, second principle that is important for us. This is the first principle. Second principle that is of importance for us is suppose we have a manifold. And suppose that we have a vector field on that manifold. And suppose that we have an initial point. And suppose that alpha is the maximal integral curve. So alpha is the maximal integral curve for V and I should really specify the interval here. This is the maximal integral curve for the vector field V and the initial point M0. And then suppose that so in particular, we have that alpha of 0 is M0. And apart from that, the velocity vector of alpha is given by the vector field at the particular point that one is at. Now, of course, what we could do is we could look at another point, say alpha of S. And we could wonder, what is the integral curve of alpha? What is the maximal integral curve of alpha with initial point alpha of S? Right? Well, the idea is that basically one can use the same curve but reparameterized in such a way that the new curve has at time t is 0 gives this particular point. And the way to do that is apply a translation in time. So let's write down beta. Beta of t is given by alpha of s plus t. So assume that S is an element of the interval of definition of alpha. So let's write I sub alpha. Define beta of t to be alpha of S plus t. And then, of course, a natural domain of definition is a translate of the interval of definition for alpha. So define the interval I of beta in such a way that if you apply S to an element of this interval, then you will cover this interval. So this means that it should be the translate of I alpha by minus S. Is that right? Since S is an element of I alpha, 0 will be an element of this interval. And if we look at beta of 0, then we get alpha of S. And if we take the derivative, the ddt of beta of t, then it's really the ddt of this, and then we can apply the chain rule, so we get the derivative of alpha times the derivative of s plus t with respect to t, which is 1. So this is the same as the derivative of alpha in s plus t by the chain rule. But alpha is an integral curve for the vector field v, so this is the v of alpha of s plus t. But this is the way we defined beta, so this is the same as v of beta. And now, thank you, of beta of t. And so this means that beta is an integral curve for the vector field v. And it's quite clear, you can go back and forth, and in this way you see that beta is actually the maximal integral curve. Because if beta had a bigger domain of definition, then of course alpha should have had also a bigger domain of definition. So this is the second principle, that the beta defined in this way is the maximal integral curve. So this beta is the maximal integral curve for the vector field V and the initial point alpha of S. And let me remind you that this maximal integral curve always exists and is unique. And so that means that if we have two ways to produce maximal integral curves, then we can compare them. And if they are integral curves for the same vector field and the same initial point, then the curves have to be equal. And this means that we can derive identities by using these general principles, and this is exactly what we are going to do. Now, yes, sure.
I didn't see it so well on the web course, and the interval I also smaller than I beta here?
No, it's not. It's really it's a translate.
It's a translate. So they're
yeah.
equal. So why
they're not equal. So for instance, one could have this interval I alpha, and then there could be this point S, and then I beta would be obtained by translating the whole interval over minus S. So it would be moved to this one, and this would be I beta.
Yes, but I don't understand why beta is maximal integral curve and alpha is not. Like why beta is bigger?
No, alpha is a maximal integral curve to start with. But then we do a reparametrization, and then we get a new maximal integral curve for the same vector field, but for a different initial point. I mean, if you have any further questions, we can discuss this in the break.
So,
yes.
We didn't have maximal integral curves in our course on manifolds, but I understand the definition. But I have one question. Can you give an example of a maximal integral curve for which the biggest domain of definition isn't the entire real line?
Absolutely.
Okay.
I can do this. But I would have to think a little bit about it, and I don't want to spend the time here to do this, but we'll discuss it in the break. Yeah.
Thank you.
So actually, if one really needs it's really special for the maximal integral curve to have all of R as domain of definition. For instance, on a compact manifold, this is always true. But on a non-compact manifold, this need not be true. And you can imagine why. Okay, let's take a compact manifold, let's take a vector field, and we have an integral curve. And now we pick a point of the integral curve and we leave it out from the manifold. Then clearly there the integral curve has to stop. Right? So you see that there are examples in abundance, really. Okay. So one really has to do something to show that the maximal domain of definition is all of R, and we will see that Lie groups give us a situation where such integral curves always have R as a maximal domain of definition. The idea is to introduce on a Lie group the notion of left invariant vector field. So the vector field V, vector field on D, is called left invariant if, definition, if for all elements x in the group, one has that take left multiplication by x. This is a diffeomorphism from the manifold G to itself. And then we can apply the push forward under this diffeomorphism to the vector field. And then what we want is that this is the same vector field again. So the vector field should be invariant under transportation by left translation. Now, of course, this can also be written out in formula. You can find it in the lecture notes. But this is the... actually, we are going to use this formula anyway, so let me write down what this means. This means that in each point y, these should be equal. And so what's the value of this vector field in y? Well, then we have to translate y by x inverse, because we have to take first we have to go back by the inverse map, then we may apply the vector field, and then we may apply but actually now I arrive at a formula that I don't like very much. It's better to draw a picture here. So we have our Lie group G. And now suppose that we have a point y and we have a point xy. Then the two are connected by left translation. The tangent spaces are connected by the tangent map at y of this left translation. And now what I want is that the tangent vectors are also, that the vectors are also connected. So that will give us the formula that if we take v of y and apply the tangent map of left translation to it, then we should obtain v at xy. And substituting an element here will basically give us this identity, but one has to do some modifications in order to really arrive at this particular identity. But this is the identity that I like most for our purposes. Good. I had difficulties understanding your question from the back.
Is it like, yeah, I have difficulty to see what is happening there.
Right. So we are in the same situation now. Okay.
It's like saying that all the curves that have V as a tangent, they are like straight. Line, not like it always has the same.
No. For instance, think of the circles in the plane. Well, then you can make a vector field pointing in all these directions, and so the circles can be realized as integral curves of a vector field. Right? Let's this. But I think it's better to discuss this in the break. Yeah. Good. So this is the definition of a left invariant vector field, and from this formula you see already that a left invariant vector field is basically determined by one particular point of the group, because all other points of the group can be reached by left translation. And then of course it's very natural to pick the neutral, this special element of the group, as our point of reference. So a way of saying this is that let's write V sub L of G to be the collection of vector fields with the property that V is left invariant. Then this is a linear space. So easy to check that the condition that vector fields form a linear space and the condition of left invariance is stable under both addition and scalar multiplication. So this is a linear space. And now saying that the left invariant vector field is completely determined by its value at the identity element is the same as saying that the map, the evaluation map, so assigning to such a vector field its value at the identity element is an injective linear map. So this is a map from the left invariant vector fields to the tangent space at the identity element, and this is injective and a linear map. Lemma. So this is quite obvious. Almost obvious, but not completely, is the statement of this lemma that this map is also a bijection, so that it is also surjective. So what is the proof? Well, the proof is as follows. Let x be a tangent vector at the neutral element. So this is G, this is the neutral element, the identity element, we have a vector x, and now I want to define a vector field, a left invariant vector field, which produces x at the identity element. Now there is only one way to define it, right? At a point x, the only way to define the vector field is by taking left translation, which maps the identity element to x, take its tangent map and apply this to x. So take the tangent map at the identity element of L sub x and apply this to capital X. Right? So define the vector field V sub x at a point x to be the tangent map at the identity element applied to x. Then if x is the identity element, left translation by the identity element is the identity map. The tangent map of the identity map is the identity map of the tangent space at E, so this will produce x again. And of course it is quite plausible that this vector field is left invariant, because we have produced it by the rules of left invariance. Well, there is one complication. Left invariance tells us a bit more. So here this is left invariant with respect to the identity element. But we want to have left invariance with respect to any pair of points. So this requires a proof. The proof can be found in the lecture notes, and it is a simple application of the chain rule for tangent maps. So the chain rule in the context of differential geometry. In the second lecture of today, we will see a number of applications of the chain rule. So I prefer to discuss the chain rule in that context and apply the chain rule in that context. And if you've seen that, you will see how to do it here too. So using the chain rule, one sees that V sub x is left invariant. And using the fact that the multiplication operation is smooth, one sees that this is a smooth vector field. Of course, this also has to be checked. V is smooth. So this is basically the proof. And now the idea is that we have a way to start with an element of the tangent space, produce a smooth vector field by using the integral curves. We get a movement on the Lie group, and we're going to use this movement on the Lie group to get away from the identity elements. And this will allow us to define the exponential map. Now there's one problem. We have no information yet about the domain of definition of the maximal integral curves with respect to these left invariant vector fields. So the thing that I'm going to prove now is exactly that lemma. So lemma so let x be a tangent vector at the identity element, then the maximal integral curve, which I'll denote by alpha sub x, for the left invariant vector field determined by x, v sub x, and the initial point, the identity element, has domain all of R. So the domain of this maximal integral curve is R. So for maximal integral curves of left invariant vector fields, we do not have to worry about the domain of definition. That's the point. Proof. So let I sub x be the domain of alpha sub x, and let S be a moment of time in this domain. Now we are going to consider two curves. The first one is the curve beta 1 of t is, well, apply alpha x of t and multiply with alpha x of s. And secondly, consider the curve, and the domain of definition I1 is just I of x. This is of course the natural domain of definition here. We may also consider beta 2 of t is alpha x of s plus 2. And now the domain of definition is ix minus s. These are the two constructions that we applied in general to integral curves for vector fields. Here we use, this is really left translation by this particular element, which is a diffeomorphism applied to alpha x and evaluated in t. So we know that beta 1 is the maximal integral curve. Principle 1 tells us beta 1 is maximal integral curve for the vector field pushed forward under this diffeomorphism, v sub x. But v sub x is left invariant, so the push forward is the vector field itself. Right? Now we are going to apply the second principle. And the second principle tells us that beta 2 Well, I haven't finished applying the first principle. The first principle tells us that, I have defined it. Yeah, I have really applied it. I've really shown that beta 1 is the maximal integral curve for the left translate of this vector field, which is the vector field itself. But I should say, of course, for which initial point, and the initial point is alpha x of s. And now the idea is to apply the second principle, the second general principle, to the curve beta 2, and then we will see that beta 2 actually is so now we apply 2, and then we have that beta 2 is the maximal integral curve for alpha x as well, but with initial point alpha x of s. So it is the maximal integral curve for the same vector field and the same initial point. Yes, there's two questions.
Well, the same question, shouldn't that be that alpha x be v? Yes. Should be effective.
Thank you. Absolutely. Alpha Vx for the left invariant vector field Vx, but with this particular initial point. So the two maximal integral curves are equal. In particular, this means that their domains of definition should be equal. So in particular, I1 is I2. Now, I1 is Ix, and I2 is Ix minus s. So what we have shown is that for all s in Ix, the interval Ix is equal to its translate by minus s. Now 0 is contained in I of x, so we can use both positive and negative numbers to translate. And by applying all these translations, we see that the interval actually has to be invariant under translations. So this implies that I of x has to be all of r. There's a question.
What if the interval is only 0?
The interval, maybe I didn't say this, I think I didn't say this. The interval is always required to be open, so this is not allowed. Yeah, thanks for asking this question. So we require that the interval of definition of an integral curve is open. But there is another important fact. So now that we know that the domain is everything, we don't have to worry about the domain anymore. And then let's have a look at what we established. We established the identity of these two elements. And that means in particular that we have this equation for all s and t in the interval of definition, which now is for all s and t element of r. So for all s and t in R, we have that alpha x of s plus t is alpha x of s times alpha x of t. Now this very much looks like the property of an exponential. Okay. Before defining the exponential map, let's look at one important example. And the example is the example of the general linear group of invertible linear transformations on a finite dimensional real vector space V. So V is finite dimensional vector space defined over the reals. And then this is the group of invertible linear transformations from V to itself. Last time we saw that this is an open subset It's an open subset of the space of all linear transformations from V to itself. We presented it in matrix form. Now this statement is equivalent to the statement in matrix form if we fix a basis, a linear basis for the space V. So this is open. And so that means in particular that the tangent space at the identity element. So what is the identity element? The identity element is the identity transformation of V. And the tangent space at the identity elements may be identified with the ambient. This is an open subset of a linear space, and then there is a natural identification of the tangent space with the ambient linear space V. Okay. Now, so actually, I forgot to prove another statement here. Let me write down the statement. Yeah, I think it's a good idea to have a break right now. This is a natural moment for having a break. So let's have a break until 1/4 past sharp.